Alright, so to do this, we're going to relate simple harmonic motion to circular motion. We're going to relate the two together. Okay? So to do this, let's take a circle. Okay, or imagine an object on a circle. So let's say we have a mass, for example, on a string with a certain radius. We're going to have it go in a circle. Okay? Now what I want to do is I want to take this two-dimensional case and I want to visualize it as one dimension. So I want to take this two-dimensional situation and visualize it as one. So imagine, for example, we're going to shine some light on this. We're going to shine light on this, and what that will do is this will produce a shadow back here, let's say on some screen. It's going to produce a shadow back on the screen. So for example, at this point, there's going to be a shadow back here that looks kind of like this, okay, back on the screen. Now as this moves, we're just going to kind of follow the shadow. So for example, if we're located like right here, this would produce a shadow like right here. And as it's moving around, this is going to produce our shadow in this direction. It's going to be moving this way. So when we're right here, for example, this would be right here. And as we're moving this way, it's going to again produce a shadow, shadow, shadow. When we get to this point, we'd have our little shadow right here, right? Okay, and then it's going to keep moving in this direction, and now it's going to just go back this way. Right? It's going to go back. When it's right here, it's going to be right here again, and so forth until we get to the end. So it'll be right here. So in other words, if we could watch this circle, this going in a circle, what we would see here is this object going back and forth and back and forth and back and forth. So this would be our spring situation. This would be what you'd see in a spring. When I oscillate this on a spring, right, you're seeing this going back and forth and back and forth. Alright, so we're setting up kind of this similarity between the two situations. Okay, so if I wanted to find the period, so when I say period, what do I mean? So we've used this term before. This is the time for, with circles, we'd say it's the time for one revolution. For objects in simple harmonic motion, we typically say the time for one cycle. So the period would be the time it goes all the way around here. That would be the same as the time to go back and forth in our one-dimensional case, go back and forth. Anyone remember how we go about finding the period for a circle? So remember we said velocity is equal to 2 pi r over t, right? Velocity is equal to 2 pi r over t, where t is the time for one revolution, right? The time for one cycle. So that's how we do it for a circle. We're now going to kind of relate this for springs. Okay, so for example, this has a velocity here, right? At this point, it'd be going completely vertical. Now, if I were to show this on my horizontal motion, what would be my horizontal velocity at this location? If the velocity is all vertical, what would be my horizontal velocity at this location? 0, right? So the velocity here would be 0 because, well, it's all vertical in my circle. Now as it starts to move this way, it gets an increased velocity, horizontal velocity, this way until it reaches this point. Well, at this point right here, all of the velocity is horizontal. So this we could think of on our graph, this would be kind of our maximum, our V max right here. Then as we start to move this way, it's going to start decreasing until at this location it's equal to 0. So you can see this is exactly the same thing we just did with our spring, where we had the 0 at the peak and the maxed value right here. Okay? Well, let's use an energy concept here to relate all this together. So at this point we have all spring potential. At this point we have all kinetic. So we can say, all right, US should equal KE. Okay, and at the maximum value, this would be 1/2 kx squared. Let's call this something else. Let's call this the amplitude squared. Okay, so this would be A, would be our amplitude here, because that's the max. X means, well, it's changing, so it could be X could change at different locations. So let's just be clear. It's the maximum value A. That should equal what? 1/2 mv squared, where V is, well, that's that V max right here, right? Also the V max, which in the case of our circle would be the total V that we have here. So anyways, if we rearrange this, we're going to get V equals Ka squared over m square root okay, and a lot of times I'm going to pull out the a here. So what's the square root of a squared? A. So I'm going to write this as square root of km times a. And now let's just set these equal to each other, these two v's. And again, what we're trying to figure out is, well, what is the period for a spring? This is the period for a circle. This is the velocity for a spring. Let's equate these to each other. So we're going to have 2 pi r over t equals square root of k over m times a. Is there a relationship between A and R?
Yeah.
They're the same. Look at our picture. So from here to here, this is R. From here to here, this is A. So R and A are the same, right? So, you know, however you want to do this, I'm just going to call this A. What happens? The A's cancel, right? So what are we left with? Let's just rearrange this and solve for time. Time is therefore equal to 2 pi square root of m over k. So TS is the period for a spring that's in simple harmonic motion. So in other words, that's the time for one full cycle. That would be the time it takes, just like this is the time to go in one circle, that would be the time it takes to go back and forth. So the time for one full cycle. Okay? So notice, what variables are important here? Mass. And what else? Spring constant. Okay? So why is mass important? So let's just do, let me just show you a quick little demo. So here we have the mass of our 50 gram mass. I'm going to put this on here. I'm going to let it start oscillating. Okay, so it's oscillating with a certain time. Right? It's going back and forth. So again, the time would be the time for one cycle. So back and forth before it repeats. What should happen if I put a larger mass? Okay, the mass should, the time should be longer. Okay, so it should be longer. In fact, if this is 50, this is 50 and this is 200, how much longer should it be?
No, 2 times.
So the mass is 4 times larger, right? 50 to 200, it's 4 times larger. However, look in the equation. it's square root of m, right? So how should the time increase? Twice. It should be twice as long. Okay? So let's just go ahead and prove that it is longer. Okay, so here's this one, right? So get an idea for the time. You're going to do a lab later where you'll actually, put numbers to this. Let's do a 200, just so you can see conceptually. Okay, so you definitely can see the period has increased. And in fact, how much longer should it be? Twice as long, right? The time should be twice as long here. So, why? Why does increasing the mass make the time longer? And I'm talking conceptually, not like mathematically. Yeah.
Is it because it's heavier and then gravity pulls on it more?
Well, I'm doing it vertically in the demo, but the same thing would happen if it was horizontal. So it's not gravity necessarily. Yeah.
The spring force needed to move it, like to oppose the other force, is increased because the mass is increased?
Kind of. You're on the right track, but think of it inversely to what you just said. What happens is the mass goes up. What happens to the acceleration if the mass goes up? Acceleration goes down. So if the acceleration goes down, what happens to its velocity? It's also going to go down, right? And so if the velocity is going down, then what should happen to the time? It should take longer. Okay? It should take longer. What about K? How is K affected? If I have a stiffer spring, what should happen to the time? Should decrease. Why should it decrease? There's a greater force acting on it. If K is up, there's a greater force. If there's a greater force, there's a greater acceleration, and therefore there's going to be a shorter time, right? Notice what's not a part of this. What got canceled out in the derivation? The amplitude, okay? So this is kind of, a lot of people, this is counterintuitive. So in other words, the time doesn't matter about the amplitude. So if I barely pull it down, it has a certain period. Okay, and if I pull it down farther, it has the exact same period, the exact same time. Why? Why is the time the same? Why does amplitude not matter? Say it again. Work through the logic. What about higher velocity?
The acceleration would be larger because there's more force acting on it.
So if I pull it down more, there's more force acting on it, which would mean more acceleration, which would mean more velocity, and but it's the same time.
Oh, same time.
But there's more distance.
But there's more distance to travel. Good. So even though the force goes up, velocity goes up, acceleration goes up, but there's more distance to travel. And the flip side would be if there's less distance and less velocity. And in the end, it all works out, right? It's going to be the exact same thing. Okay, so anyways, let's finish this up. So here's our period. There's a couple other terms I just want you to understand. The next one is called frequency. And actually, we've dealt with some of these with respect to circles. We're just going to relate it with respect to springs. So frequency, what is frequency? With circles, what did we refer to as a frequency? How many cycles per time? So we often did this with like revolutions per minute, right? We'd say, okay, there's 100 revolutions per minute. That's telling you the frequency of it. Okay? So frequency is essentially the number of cycles. And it could be revolutions. Like with circles, we'd definitely be talking about revolutions. With springs, we're going to be talking about cycles per time. Now, we did a lot with RPMs. The true unit should be seconds. So this should be cycles per second. This gets renamed as a hertz. Hertz. So whenever you hear hertz, what they're talking about is cycles per second. Computers oftentimes use hertz to talk about speeds. Like, for example, if you have a computer that goes 3 gigahertz, well, that basically means that your computer goes at 3 times 10 to the 9th cycles or calculations per second. So that's how fast, how many calculations your computer is making in a second, about 3 billion if it's at 3 gigahertz. What's the relationship between frequency and period? They're inverse relationships, right? Period is the time per cycle. Period is time per cycle, right? And what is frequency? Cycles per time. So the relationship is a nice one. F should equal 1 over T. Okay, there's one more term that we use a lot. Oh, so what would the frequency be here? How could I rearrange this in terms of frequency? What would F sub S be? Well, just reciprocate this, right? So that would be 1 over 2 pi square root of K over M. All right, last term that we use is called angular frequency. Okay, let's say, for example, I have some frequency which is cycles per second. Well, when talking about a circle, if we make one full cycle, how many radians did it take to go one full cycle? 2 pi, right? So there's 2 pi radians in one cycle. Okay, therefore, angular velocity, which we use the same symbol we used before for angular velocity and angular frequency, use the same symbol, and they really just have the same meaning, is equal to 2 pi f. Okay, so for a spring, let's go back to right here. What's 2 pi f going to be equal to? Square root of K over M.